Thank you everyone for coming to the Spark meetup. My name is Bruno. I'm a cloud platform engineer at Rokt. We run Spark on Kubernetes, and we run into some optimization issue where we spend probably a bit too much on our Spark applications. So we wanted to right-size our applications automatically. So quick shorthand first. Who here is guilty of over-provisioning their Spark applications, bumping up the memory and CPU intentionally? A few people in the room. Excellent. So this may be very useful for you. So to give a bit more context, at Spark, at Rokt, we run about 1,000 Spark jobs a day. We run all the Spark applications on Kubernetes. We operate in a multi-cluster, multi-region environment, and we process around between 30 and 300 petabytes of data every hour. We use Carpenter for the provisioning. We have a mix of on-demand and spot instances. We use Datadog for observability, and then we have a clear split between the platform team and the data engineering teams. The way we schedule our Spark applications, we have Airflow and Kubeflow for the workflow engines. People will define their workflows. They will schedule a Spark application to process the data, whether it's to generate data sets for the ML pipelines, whether it's to process the data in the data lake, whether it's for analytics. We also have data engineers submitting ad hoc Spark applications from their local. They want to test something. Everything is scheduled using the job scheduling gateway we have in the middle, which is an API that will translate the Spark submit request into a Spark application using the Spark on Kubernetes operator. The Spark on Kubernetes operator will convert the application definition into the Spark driver, and the Spark driver will then spawn executors to execute the Spark or the Spark jobs. The Spark on Kubernetes is hard to size. First, when you create a new job, a data engineer will have to guess the configuration based on the data, the amount of data they want to process. Usually they would just copy-paste the configuration from another job, quite similar, use the same value, add a comment somewhere saying, we need to tune this later. They never do. If it works, happy days. No OM, job duration is what is expected. People will never touch the configuration again. If something breaks, either the job is slow, you run into an OM, people will just go and pump up the memory request, add more calls, increase the CPU request until it works. Everything is based on intuition, not data. At scale, if you have 100 jobs or even 1,000 jobs, this is not manageable. You will have probably this configuration copy-pasted all over the place. It's very hard to address. And on top of that, if you have a dev, pre-production environment, production environments using the same config, chances are you don't have a lot of data to process in a pre-prod environment, but still using the same configuration as a production environment. So let's talk about memory management in Spark. So when running on Kubernetes, we have containers where we have the memory request set for the Spark executor container. At the Spark level, you have the configuration, the Spark executor memory, which will define the memory used for the JVM. So this will translate to the XMS and XMX value. So if you set, for instance, your Spark executor memory to 4 gig, your JVM will be allocated 4 gig of memory, whether you use it or not. It will be just pre-allocated to the JVM. Another config that we have is a Spark executor memory overhead. Usually it's defined as a fraction. By default, it's 10% or 40% if you use PySpark. The memory overhead is used for caching the file system, for NIO buffers, and a few other things. Optionally, you have the off-heap memory. So this is memory that is used outside of the JVM, so there is no garbage collection. That can be used for storing data that needs to be accessed very efficiently. Because it will bypass the GC and not use the JVM heap, it will be a very fast access to memory. And then optionally, you can have the Spark, PySpark memory as well. Double-clicking on the JVM usage, Spark will have reserved memory, which is fixed to 300 megabytes. Then you have the user memory here, that is used for UDF, for instance, RDD metadata, and any kind of data structure defined by the user. And then Spark has a concept of unified memory, which is split 50-50 by default between the storage memory, used for RDDs and broadcast variables, and the execution memory, that is used for computation tasks like shuffle, joins, and aggregation. But we have a no-M-kill paradox here, which is something that needs to be understood. So even if you set the Spark executor memory to 4 gig, everything else is indexed based on this value. So even if we set the JVM heap based on the 4 gigs to XMS and XMS 4 gigs, so it's prelocated to the JVM, even if you don't use the full JVM heap size, you can still have the memory overhead factor or anything that is off heap going over the total request of the memory for the container. Meaning, if the overhead factor is too low, the memory request for the container will be too low, and if you have processed outside of the JVM using more memory than expected, that can trigger a no-M kill or a no-M event. So what people will do in that case, they will just bump up the Spark executor memory, because everything will be increased proportionally. The JVM heap is still underused, but everything will be bumped up. That will actually cause excessive over-provisioning of the memory, and it doesn't necessarily solve the OM kill, or you have to bump up the memory quite a lot to achieve this. So the first thing you want to do when you run your Spark application is to use tools available on the market. So you can talk to our sponsor here, Datadog, DataFlint. They build amazing tools to look into your Spark applications, understand the memory usage patterns for your application, how the memory is used by the different executors, you have data skew, what you can optimize. So highly recommend talking to the people in the room here organizing the meetup. When it comes to right-sizing applications at the infrastructure level, you have different options. First, you will start doing the manual job tuning. So you will go to checking your Spark application definition, tune the memory request, CPU request, and hope it works. And then leave it there if it works, and never touch it again. People might be using Kubernetes vertical pod auto-scaling for auto-scaling workloads. This tool is open source. It's good, but it doesn't have any JVM visibility. So it's not something designed to work with Spark applications. It's more for general workloads, non-JVM based. You may be familiar with the Spark dynamic resource allocation. This one is more for horizontal scaling to add executors dynamically based on the backlog of tasks that are being executed. And then you have two options. It's either build or buy a solution. So you can build a custom Kubernetes controller that will fetch the metrics from the JVM, CPU memory usage, try to dive into the memory to understand the patterns, and then build something that will modify all the JVM parameters, CPU, memory requests for executors and drivers. It's probably a significant investment if you want to build something like this. There are some tools available on the market, like ScaleOps, HighestAI, NOps, and a few more. And at Rokt, we decided to go with ScaleOps because it provided all the functionalities we needed. So JVM level observability for the heap and non-heap. We can define pair workload policies, so we can be quite aggressive in terms of right-sizing applications, or be more conservative if we want to keep a buffer for the applications, or the critical ones. And it also understands all the JVM options that we pass to the executors, so the one I talked about previously. How we did it at Rokt. So first we built an inventory of all the Spark applications to understand how much wastage we had across the applications. Because before starting an exercise like this, we want to understand how much you waste, so how much you can cost optimize, and is it worth it? After that, we did an audit of all the JVM configs we had across the different applications, and understood there was nothing standardized, so very hard to fix manually. We established a baseline, so using Datadog that we use for observability, having the metrics for across all the jobs. We could monitor the job durations, actual OM kills that we have for the application, checking the stability, and what was the baseline or the current usage, and how much we could optimize by. Then we run scale-ups in recommendation mode for this Spark application that will give us some data, explaining how much we could optimize in terms of resources, and also putting a $ next to the cost optimization. Then we did a progressive rollout, starting with less critical application, prove the tool works, engage with data engineering teams, which is very important, because this will start modifying the parameters at runtime of their applications, so they have to be kept in the loop. And then we decided to fully roll out the solution, so all the Spark applications we run at Rokt are fully right-sized automatically. There is no more engineering effort required to set the CPU and memory request for the applications. And we also combine this with Spot instances. Because we right-size applications down most of the time, we run on smaller instances that have less chances of Spot interruptions. So now we can be a bit more aggressive migrating Spark applications to Spot instances. This is scale-ups. So that's an example of one application for one run that we have. Top left will be the CPU usage. The red line is the original request we had at the container level, and the green one is what is recommended by the tool and changed when the pod is scheduled on the cluster. Here's same thing for memory. So you can see the blue line here is actual usage, green line is much closer to actual usage compared to the red line, the original request. So we went from a request of 320 gig of memory to something around 110 gig. So it's a massive difference. And then we have some more data around the JVM heap usage as well going up. So every time we have some data shuffle operations, we expect the memory to increase like this. Across multiple runs, this is what it looks like. Same job being scheduled, I think, every few hours. Interesting fact is to see the green line here. So the recommendations for the memory requests are evolving or adjusting over time based on the actual job usage. Looking at across multiple jobs, multiple runs, we created a Datadog dashboard for us to look at the jobs. So checking that job's complete, checking failed jobs, which usually means something is going really wrong. Having a look at the job duration as well. So we have some monitors in place to make sure that the job duration time is not impacted. And we also look at OM events. So because we're a bit more aggressive with the memory resizing, we know that if all of a sudden there is a change in the pattern of data usage, this can spike and go over the actual memory request. Scale-ups will detect this, having an OM event, and will bump up the memory request straight away. So when the executor fails and being rescheduled, it will have more memory allocated automatically. So results set your chart. First, decrease CPU and memory request by 30 to 35% in production, which is a big win for the team. We have self-healing OOMs. So every time we have a Spark application having an OOM, before that people will have to go do some troubleshooting, update the configuration, deploy to production. That will take time. Now it's self-healing automatically. Executor OOMs gets cleaned up, reschedule with more memory. Spot plus rightsizing, the savings are compounding, as I was explaining, because now we can be more aggressive, moving more stuff to Spot instances. What we learned as well is to segment your policies. So when you do rightsizing policies, usually you will take a percentile of the CPU and memory usage based on the historical data point. So you can be very aggressive and take the 90th percentile with a buffer, or you can be more conservative and take the maximum value observed over the past 7 days. So you can define your policies this way based on the type of the workloads. Data skew, that's something that we're still trying to address and trying to optimize. If you have data skews, so some of the partitions may have more data to be processed, it means executors processing these partitions will have more work to do, process more data, takes longer to run. meaning this will skew the memory request for the end percentile you want to use in your policy. Meaning everything, all the executors will be over-provisioned based on the one that is doing the most work. Also surfaced some of the observability gap we had in our solution and improved our understanding of the Spark memory management. So key takeaways for you. So Spark sizing creates invisible compounding waste, especially at scale with no feedback loop. So if you just deploy applications, you're wasting resources you don't even know. So you need to check actively this is happening. Automate the loop between observe, recommend, and apply. If it's fully automated, it's not a problem anymore. Start to observe first, prove there is a gap between the actual usage and where you want to be at. Measure this and build a case internally to fix it and claim the win. Understand your workload as well. All the workloads will be different in terms of data usage, memory, CPU usage, job duration, how many executors, you have dynamic allocation or not. All this is to be included in your scaling strategy. And right-sizing just one layer of the cost optimization strategy. So you also need to look at optimizing your applications, moving to spot instances, moving to Graviton or cheaper hardware, or do other things to cost optimize your Spark applications. That's it. Any questions?
Thank you, Bruno. Is it on? Yeah, okay, you gotta speak closer to the mic. I think what I see in the two things where you have massive jobs or you're trying to scale to, what was it, 300 petabytes a day or hour. What I'm interested in is, do you run into things of such as OOM, out of memory errors? And the other thing that I've seen working with the GC and also with the CPU allocation is thread starvation. Do you see any of this in the experiments that you've done with this framework?
We haven't run into thread starvation for our Spark applications. Probably because we've been using quite large instance sizes with a lot of CPUs. Although we have seen CPU thrashing because of excessive GC. It was probably very specific to some of the jobs that we have. We also have seen a lot of speeding to memory and to disk. So it depends. You have so many different combinations of things that can happen. It's always job by job that you want to analyze the behavior. It's hard to, but yeah, we haven't seen that too much actually, thread starvation.
Okay, thank you.
Awesome. I use the fact that it has a microphone to also like add some insights. Apache Spark is used by OpenAI to like answer like when you send like batch jobs of like doing inference, like it's using Apache Spark. Apache Spark is used to train like the huge models like the LLMs in NVIDIA and other companies. Like Apache Spark is like using the highest level of any distributed processing. You do get like starvations and this kind of like issues in specific connectors, like JRVC and such. But overall, like the system is like battle tested, 20 years of like code. There are advantages to move to Rust-based systems that are newer and more exciting, but Apache Spark code is very bad. What we have in the cool. More questions? Yes.
I was just curious, did you take cost into consideration for this? You mentioned that you used scale-offs, which as far as I know is not a free tool. So did you ever benchmark how much you're paying for that versus how much savings you're getting on the other end?
Absolutely, yes. So we did an analysis of the market between the open source tools and the different vendors. So yes, scale-offs is a commercial product. And we started a POC at Rokt about a year ago and targeting non-production environments. POC was successful, so we deployed the solution in recommendation mode in production. And that confirmed the analysis that we did to understand how much we could optimize. So the scale-ups figures were matching what the figures we came up with internally. And that gave us enough confidence to pull the trigger and engage with scale-ups and get a bigger contract for production. But yeah, you probably want to do that progressively and make sure that you will realize savings before purchasing a licensed product. Yes.
Yes.
Hi, just a quick question. You mentioned OpenAI and the LLMs, but are you guys using AI agents to like increase the number of pods, change the number of executors, workers, that sort of thing, job scheduling?
We have some initiatives internally. Everyone wants to do AI these days. We do as well. It's very early stages. We use AI mostly for some ad hoc analysis, like I want to analyze this job to understand how we can optimize this, or find the jobs that we could potentially move to spot instances based on the job duration, the nature of the job. But we don't have something fully automated using AI. I guess many can talk about this.
Yeah, we have something internal DataFlint about product. Like super new, super challenging. Like the market is mostly on reactive agents, like using cloud code when you need to code something. Proactive, like agents that looks at your environment and act on it. It's super new. A lot of unsolved problems like human in the loop, coding, and more. Happy to chat about it. I haven't shown it today, but it's like also something we like to part of it. Cool. Last questions?
The pushback that I usually get when it comes to rightsizing is that the engineers say they might need it sometime down the road, and it doesn't matter what the last 7 days of usage look like, or 30 days or even 90 days, but they refuse to downsize it or rightsize rather, because they need it sometime down the road. But in the meantime, all the oversized resources continue to incur a lot of costs, so I was wondering like, how you can deal with that situation.
We run into these kind of issues as well. So it's, yeah.
Shrink it up, and then when they need a request, they have to explain why.
Yeah, it's about ownership, and if you make the wastage visible, and if you can put a dollar value, a dollar sign next to it, and then make people responsible for it, that's where you get some traction and people see it's a problem. And especially if you come up with a fix and a solution for that, and you take care of the problem for them, they will accept the solution. But you have to build a case first, and you have to engage with data engineering team so they understand what is the value for them as well. Because you move the complexity of their hand and you put that on the infrastructure side to fully automate rightsizing of applications. So they win in the end. And if you can also explain that the jobs will be more stable because you take care of OM, for instance, automatically, they won't get paid at 2 a.m. because their Spark application is crashing.
Okay, we have a lot of demands, so do one last question. Last question.
I think thank you for the talk. I think you had talked a lot about these right-sizing these jobs with batch jobs. Does it support streaming? Because I think with streaming applications, they're kind of always running, the executor's always running, and so you don't really have insight or correctability into the or the executor memory size and all these memory configurations.
That's a good question. Actually, we do, and so we enable scale-ups for not for streaming applications, just for batch applications, and we have another cluster where we run streaming applications, and we're just starting automating them now. We also upgraded to Kubernetes 133 that supports in-place right-sizing. So we know that for streaming application, we can right-size without having to restart the executors and the containers. It's not that simple. A few things we need to figure out how to do this, but it works as well for streaming applications. In the policy defined by scale-ups, there is a way to restart executors. So you can actually define a schedule to say you can disrupt executed executors once an hour, once a day to apply the new policy. So if your streaming application can sustain execute or restart, and it should, if it doesn't happen too often, you can actually right-size streaming applications as well.
But like a streaming application can go up and down in data volume, right? So
Yeah.
can scale.
So it's your policy. When you define your policy, so you define the loopback period that you want to use. So it can be an hour, a day, a week, a month. So you define based on your application, and then your policy can be very aggressive. I just want to adapt to short bursts, or I want to be very conservative and take the maximum value seen over the past 7 days.
Maybe I understand that the question differently. You mean like horizontal, like increasing and decreasing the number of machines, or like vertical?
I mean, if you're like having events, right? You get a lot of events during the daytime and then nothing, no activity at night. Like you're over provisioned during the day. During at night and then.
Super cool.
Yeah, I actually can take it because we see it a lot. So you will be surprised, but there is no solution currently in Apache Spark. Basically, it's a dynamic allocation algorithm that when the scaling doesn't work, the streaming. There is a secret one, not documented, that is a bit better, but it's buggy. It's called dynamic allocation streaming. It's not documented, it's in the source code. You can enable it, but it's super weird. Databricks and the Spark community try to fix it with the new declarative pipeline. It's super new, it's in RC, like Databricks give it like to only service customers, so they're working on a solution. At the moment, there is actually no solution for it, besides like moving to Apache Spark. So that's a knock-on issue, and hopefully it gets solved soon. Cool. Thank you, Bruno.
Thank you.
Yeah, feel free to stay. We have like some more time, like to mingle. That's part of the fun. We have more beers and more snacks. So feel free to take home. We have some extra. And hoping to see you next meetup today.
Yeah.